EECS 281, lecture number 11, Quicksort, spring 2020. So our cover slide here has a nice graphic that shows part way through a quicksort. It'll be a little bit easier to understand after we go through today's lecture, but it's what's going on there. Yesterday we looked at our elementary sorts. Today we're going to try to fix a couple of problems that all of those elementary sorts had. First problem was the vast number of comparisons. They might compare every pair of elements in those sorts. And you're only learning one piece of information from any given comparison. This one is less than that one. That's all I know. Think about how binary search works. When you do a comparison in a binary search, you learn something about half of the items, right? One comparison is that if I didn't find the value, it's either less than this, and half of those above me are written off, or it's greater than this, and the other half below me is written off. So that one comparison gives a lot more information in a binary search than it does when we're doing our simple sorts. The other thing, too, is the simple sorts really focus on getting one thing corrected, one inversion corrected. So you can think of moving one element at a time, and that's about it. So even if the element is far out of place, it still moves it. If you look at selection sort will take an element from the other side of the container and move it into position. So that's far more effective in terms of motion. But selection sort has its own drawbacks, right? So we'll look at the faster sorts to sort of attack these two problems. And today it's going to be Quicksort. Quicksort is pretty easy to implement. It's great because it works good with average data and obviously anything better than average case data. As it gets closer to best case data, it continues to work well. It does, however, sort of tail off as we get to worst case data, and we'll talk about that extensively. The other good thing about it is the algorithm itself, as you look at it, seems to only take a constant amount of additional memory. However, hidden in there is the fact that it's a recursive algorithm, and these recursive calls cannot all be made tail recursive, so we will have to deal with stack frames. Quicksort is a divide and conquer algorithm. Our divide and conquer algorithms are something we'll talk about also in the future, but they take the problem and they divide it into a smaller copy of that problem and solve that problem. Anytime you've got something like that going on, you got to have a base case. And in this particular instance, the base case of Quicksort is any array of length 0 or length 1. So you can say that those are sorted. It's hard to be unsorted when you're empty, and it's also hard to be unsorted when you're all alone. So there's our base case. If we get down to a range that's 0 or 1 long, we can consider that sorted. We can consider our sort successful. We can stop trying to divide and conquer any further. There's an inductive step that happens as well in the divide and conquer. And in that one, what we're going to do is we're going to find some element that we're going to use to partition the array. And here it's just called ELT, right? By the time we get done with our partition, our array is going to look something like this. It's got an ELT, which is in the middle, let's call it quote middle, somewhere in the middle, and then there's a left-hand side and a right-hand side. And the important thing about this partition is where the ELT sits, everything to the left of it is less than or equal to the ELT, and everything to the right of it is greater than or equal to the ELT. What that means is, once I've partitioned this array, I don't necessarily have the things in the left-hand side being sorted, but I do know that they're all less than ELT. Same thing with the right-hand side. They're not necessarily sorted, but the ELT is less than all of the things in the right-hand side. So after a partition, you can imagine that ELT is exactly where it belongs. It's never going to move because even though the things to the left of it are unsorted, if there's 4 of them and ELT should be in the 5th position, it doesn't matter what order those first 4 are in if the ELT is in the 5th position, and so on. So once we've got that done, we can say, well, ELT is where it belongs. All we have to do now, since we have divided this, is conquer, and we'll recursively jump into the right-hand side. And full, it's short. We see it's a recursive algorithm. Already we've got Quicksort, the name of the algorithm, and 2 calls to Quicksort here. So we can see that possibly this call in line 6 could be tail recursive. It is the last thing to occur here in Quicksort. So this could be tail recursive, but there's no way I can make the call in line 5 tail recursive because there's always going to be the line 6 call to be done after that. All right, so it's a recursive algorithm. Of course, we start with our base case. We already described what that was. This is when my range is length 0 or 1. You can see here that since left and right are indices of what I'm sorting, we're going to look at this through a C-style array lens. But if left is an index where the sort begins and right is an index just past where it ends, similar to the way that we look at things for the STL, left is an index, and if I square brackets that, I should get data, and if I square brackets right, I should not get data, or I should at least not be messing with the data that's there. So in this case, then, as I look at left plus 1, if that's greater than or equal to right, that is equivalent to my range being size 0 or size 1. Right? In that case, I return, and I'm done. Then all the magic happens in line 4. Get this pivot, which is really what ELT is called in this piece of code. Get this pivot by doing a partition of A, starting at left and ending at right. So this is a call out to another function. That's where all of the work gets done. Other than that, this is all of Quicksort. So it's great. I'm going to have to keep recursing in here, but this is going to make it happen. So partition is how we get this. The question is, how do we form this left-hand side followed by ELT followed by right-hand side? We're going to keep dividing and conquering, and ideally we would love that ELT to be the median. If the ELT was the median of the container or the range that I'm sorting, then there would be as many items in LHS as there are in RHS. That's going to be the best for me because over the life of the sort, if I'm always dividing it exactly in half, I've got the least number of divisions. All right, so since the median is the best, why don't we just use that? I think by now we've all had a chance to look into median just a little bit, and in order for me to get to the median, I've got to have sorted data. So if I need the median to sort data, but I need sorted data to get the median, I'm stuck now in a recursive loop that has no base case. So I can't just use the median. What I'm going to do then is do the next best thing, which is pick something at random. I know that doesn't sound great. See, I would like something very focused like a median, but since I can't have that, I'll just take anything. But that's what we've got to stick with, because if the array is in random order, chances are, just like our average case analysis on linear searches, I'm going to get something that on average is the median, right? So sometimes it'll be less than the median, sometimes it'll be way less than the median, but other times it will be slightly greater than the median or even much greater than the median. But over the life of the sort, as I keep picking these things at random, I will have this average case that works out to be something like me picking the median. So you can say that I'm never guaranteed to get a good pick, and this quality that does get averaged over all of these choices is great. However, there's still room for a worst case, right? In the worst case, I always pick a bad choice. You're not guaranteed to get any one good pick, but if I get multiple bad picks, then life isn't great. That's where Quicksort has its shortcomings. So for this example, what we're going to do is we're just going to pick the last element in the range to be sorted. And that's just very efficient for us, and we'll see why. So as I pick the last item and say, this is going to be my partitioning element. There it is. It's 6. So what I'm going to do after that is look from the left-hand side for anything that is greater than 6, because that's an element that is out of place. And once I find that, I'm going to look from the right-hand side to find some element that is less than my pivot, because that's out of place. Then once I've identified something that's too big in the small zone and something that's too small in the big zone, I'm going to swap those two things. So I accomplish more than one fix with that, right? Because you can think about them as being inversions with relationship to each other, but they're also inversions with relationship to the pivot, because the thing to the left, the big thing in the small zone, that is greater than the pivot, and the thing to the right, which is the small thing in the big zone, that is less than the pivot. So both of them are out of place with each other, but they're also out of place with the pivot. All right, so I'll start out sort of just chugging along here with my left pointer. And my left pointer is going to be looking at 2. 2 is less than my pivot 6, so 2 is in good shape. I'll move on then. How about 9? Well, 9 is greater than my pivot, so that's my candidate for swapping. Now I just need to find its partner. So I'll leave that left there and come in here to start checking things from the right. 8, that's greater than the pivot. It's fine. 5, less than the pivot. Now I've got my swap mates. If I swap 9 and 5, I'm fixing things with relationship both to each other and with relationship to the 6. So I'll do this swap here, and then I'll continue from where left and right left off to see if I can't fix more of this. So after the swap, it looks like 2, 5, 3, 4, 7, 9, 8. And my 6 is still over there. That's what it physically looks like, and I've just drawn that little box out there to let you know that we're sequestering that, right? When I left off, L was right here, and R was right there. Now I'm just going to continue moving until these left and right end up pointing at a range that is size 0 or size 1. All right? Right now, the range has 5, 3, 4, and 7 in it, because remember that the right is pointing just past good data. It's currently pointing at the 9, which means 9 is no longer part of this sort. So all I'm really sorting right now is this 5, 3, 4, 7. So as I move in, I increment L. L looks to be 3, and then, of course, it's less than 6. So there's a new swap candidate. All right, I'll jump to the other side, looking for something to replace this R with that has to be smaller in the big zone. So I'm looking for a value that is smaller than the pivot coming from the right. And I first see 7. That is greater than 6, so we don't mind. I next see 4. And 4 is less than my pivot, so there's my swap mate. I'm going to have to swap those things. I did this wrong, didn't I? I did. I should have kept going from left. All right. Let's clean this up a bit. Sorry. Backtracing a step. All right. So left was looking there. It found 3, which is less than 6, and that's a great thing. It's less than the pivot. Sorry. We're going to leave that there, and I find 4, also less than the pivot. Not a problem. I move in there, and I next find 7. So 7 is the first thing that is greater than my pivot. Right? Now I've got a left that's good. Sorry about that. Got off track here. My left, as I was with it here, was already pointing there. There's my right. So now I'm at the situation where it's time for me to try to move my right pointer to the left to try to find something smaller than my pivot. So as I increment R and look there, I see that I've got a 7. This is greater than 6 coming from the right-hand side, so that's a good thing. But now I've also gotten to the point where L and R are pointing at the same thing, right? So if I attempt to decrement R one more to find something smaller than 6, then my left and right pointers will have crossed, and I'll be looking at what amounts to a negative sized range. So I'm going to stop here, and this is where I break out. And what that ends up with is my partition is now set up. And to finalize this, what I'm going to do is I'm going to swap my pivot element with my left pointer, right? So that means this swap is going to take place here, right? And so what it looks like after that swap is 2, 5, 3, 4, 6, 9, 8, 7. I'm going to put a box around that pivot because, as I mentioned earlier, that pivot now is in its final position. There's no need to move this again. If you look at it, there are 4 values in this range that are less than 6. They're all to the left of it. And there are 3 values that are greater than 6, and they're all to the right. So no matter how I fix those other elements, when I get done, 6 is going to be right here at index 4. All right? Good enough. That's my divide step. Now my conquer step is, let's quicksort this half and quicksort that half. So this is where recursion happens, and I'm just trying to quicksort this 2, 5, 3, 4. So to make that happen, of course, I'm going to pick my pivot as the last and repeat what I was doing from before. With my L coming here looking at 2, 2 is less than 4. That's a good thing. It belongs to the left of the pivot. 5 is greater than 4. Coming from the left, that's a bad thing. There's my swap candidate. All right, we come in from the right, and I see that this value coming from the right is less than the pivot, and that's the other half of my swap candidate, right? There's my swap mates 5 and 3. I'm going to give them a flip, and I end up with something that looks like 2. Yeah, that's not a 2. 2, 3, 5, and I've got my pivot out there 4, right? With L pointing at 5, L pointing at 3, and R pointing at 5, right? As I continue along this route, I can see that L will identify 5 as a swap candidate. That value coming from the left, greater than the pivot, is a swap candidate. As it comes time to decrement R, though, I see that R is already pointing at L, and there is no need to move any further. So at this point, my partition has been located. All I have to do to finalize when I get done is swap the pivot with L, right? So that ends up putting 2, 3, 4, and 5 into place. Looks like that. All right, and so you can see in that divided section that my divide and conquer thing has taken place. I've got 4 in its position. The only things to the left of 4 are less than 4. The only things to the right of 4 are greater than 4. This is a good partition. It also has the side benefit of actually being sorted. But in terms of being sorted, Quicksort doesn't realize that this portion is already sorted. It thinks of this 5 as being sorted, but it doesn't know that 2, 3 is sorted. It just happens to be sorted. So we're still going to recurse into that to try to fix that, if you will. Then once we get done with this left-hand side, we'll jump in and do the same thing all the way over on the right-hand side. So let me go ahead and clean up a bit. Scroll, 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 scroll. That looks like this. All right, I've got 2, 3. No, that wasn't the way it was. I cleared it up. 2, 5, 3, 4, 6 was there. And then I had 9, 8, 7. Right? And then my next step, I came down and I said, I've got 2, 3, 4 in place, 5. All right, now I've got a little bit more vertical space here. So I'm going to continue with my recursion, which is to jump into the left-hand side, and let's make 3 my pivot. Great. As I look at this from the left-hand side, I see I've got something smaller than the pivot. That's great. I can't increment it anymore. Right? I can. So I go here, and what do I find? I find that 3 from the left is not less than my pivot, because my pivot is also 3. Right? As I start out with R starts out right away pointing at 2, and you see that they've come to the place where we've crisscrossed. So I'm going to stop here then and say, what do I do to wrap up? Is I swap the pivot with my left, which of course is the same thing. So after this step, I'll end up with something that looks like a 2 here, a 3 in its proper position, right? And now what I have is a right-hand side of length 0. So that's trivially sorted there. It's hidden, it's in my base case, but it's a done deal, right? That pivot is done. The left-hand side is all less than 3. From that range, the only things that are to the right of 3 are greater than 3, which is nothing. But now I can recurse into my left-hand side, and I can see right away that that's only of length 1, so really all I need to do is lock down 2 there, right? Then recursion happens. I go back and hit this little empty zone. That's a range of size 0. The call still gets made. Nothing happens there, though, because it's a base case, right? After that, I can start working on the right-hand side of 4. To get there, I see that the length of that subsection is only 1, so it's also trivially sorted. So from there, I'll lock down 5. And then I'm going to recurse into the right-hand side where I'm trying to deal with all of these things over here, right of 6. All right, so here we'll start out. We'll take that as my pivot. Coming from the left, I see something greater than the pivot, so that's my first swap case. Coming from the right, I see something greater than the pivot, and that's okay. And then I go back again. I see something from the right that's also greater than the pivot. Not a problem. Things to the right should be greater than the pivot. But now left and right have met, so I'm no longer going to try to decrement right. So to clean things up, all I have to do is swap left with my pivot. And so I end up bringing a 7 here, 8 and 9 like that, with my 7 being the pivot, and it is where it belongs. Once again, I've got a situation where 8 and 9 look like they're sorted, but they look like they're sorted to me. To Quicksort, they look like they still need some work. Okay? After we've got the 7 as our pivot, I'm going to recurse and jump into the left-hand side. The left-hand side is, of course, length 0, so nothing happens there. Then I jump into the right-hand side, and you can see that as I try to quicksort this 8, 9, I'll pick 9 as my pivot, and won't have any swapping to do. And my next phase will have 9 there. I'll look at 9's left, which is a length 1. I'll 8 that up, and then I'll recurse my way back up. 9's right is empty. 7's right is done. 6's right is done. And the entire array gets sorted as I bring everything down. Oh, that's down already. And I end up with 2, 3, 4, 5, 6, 7, 8, 9. So there you have Quicksort implemented. Only one major mistake, and we pulled it back together before life got too bad. So here's an example where I'm getting worst case data. I won't go through the full sort, but you can see that if I continue to do as I worked on last time, what if I pick this as my pivot? You can see that everything in that range is going to end up in the left-hand side by the time I get my partition done, and the 5 won't really move. So I'll look at this from the left, 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 and then look at that from the right and say, no chance. All right, I know that my data looks like this now. 5 is sorted, and I still have this in question here. All right, so let's divide and conquer, get the left-hand side. I'll make this my new pivot. I'll look at this, look at this, look at this, look at this. Each time I'm doing that, I'm comparing that to the pivot value when I say look at this. So this is still a number of comparisons, and then my right crosses over so I don't do anything with it, right? Once I've got that done, I say, well, really then it looks like I've got 1, 2, 3, 4 in proper position, 5 in proper position. So let's take that as my new pivot. Comparison, 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 stop. All right, and then I know that 1, 2, 3 is good, 4 is good, 5 is good. Right, but these left sweeping arrows are actually comparisons. So I've done 5 comparisons here, 4 comparisons here, 3 comparisons here. As I make this my new pivot, then I'm pretty much okay there. I don't need to go any farther than that because I've got a length of 1 on the left-hand side. But I'm still, in this case, comparing almost every element to my pivot repeatedly, right? I've repeatedly, and every level I've compared every available element to my pivot. So this ends up being something that looks like it's big O n squared. And that's why we don't like it. Right? So when I've got a worst case scenario, that's when I end up with n squared behavior in Quicksort. And you saw here in Quicksort, when I kept picking an element earlier, here 6 is close to the median. After that, when I picked 4, that was close to the median of this data set. 7 wasn't so close to the median on this set, but it wasn't too bad because there wasn't too much work after that. So this was real good average case data showing up here. I got things that weren't terrible all the time. They weren't great all the time, but they averaged out to decent. Here, I picked the worst thing possible. I always had something where one sort of my conquer sections had n-1 items in it. So I started out trying to sort 5 things, and after one step, now I still have 4 things left to sort. After that step, I still have 3 things left to sort. Then I still have 2 things left to sort. So in this previous version, I was making more things go away as I put my partition in there. Here, I was only making 1 item go away. All right, so worst case here, I'm picking something that is not my median, that is taking it, and I've got one of my left-hand side or right-hand sides is empty, and the other one has all the stuff in it. All right, the part we've all been waiting for, that code. This is what I just walked through with my red arrows. You can see here that the partition call starts with data in A. We know where to start in the data and where to end. So there's my 2 boundaries, right? And we start out by identifying the pivot as what's the rightmost data item. So since we can't dereference right as it comes in, we have to decrement it first. That moves right back 1. So now I can actually square brackets at right. So now I know that the pivot index is at 1 less than the right that came in. So the last good data item. Then I jump into this while loop, and this while loop is just going to keep going as long as what's in left, this while loop keeps going until I get out of it, right? I'm going to break out of it here. We see that this is the only way that I get out of my outer while loop, right? This is a while true, and I'm going to keep going as long as left is greater than or equal to right. I said that backwards. As long as left is less than right, I'm going to keep going. As soon as left is greater than or equal to right, I break out. All right, so that's how I get out of my outer loop. Inside there, I've got a couple loops, and this loop just gets my left index updated. This loop gets my right index updated. You see that when it's successful, this increments the left, and when this is successful, it decrements the right. So that's moving those arrows that I was using to find swap mates. As long as the value that I'm looking at from the left is less than a pivot, I say that's great. You should be over there. I'll keep moving left inwards. Eventually, I run into an element from the left that is greater than the pivot. When it's greater than or even equal to the pivot, I say that's something that I am going to swap out of this position. All right, so I'll stop doing my plus plus left, and when I get out of this while loop, left is pointing at my left swap candidate. Then I run this same thing again here coming from the right. You see now I need to make sure that left has to be less than right. So that's part of my while loop. As well, I'm trying to find something from the right whose value is not less than the pivot, right? So here, if what's coming from the right is greater than or equal to the pivot, then that's going to be my new swap candidate. If it's less than the pivot, it's going to be my new swap candidate, right? Otherwise, I'm going to just decrement my way past that. So when I'm done with these 2 while loops, left and right are pointing at the things to be swapped. There we go. If they're pointing at unique items, then I'm going to do a swap here. You see that swap left with right -1, and we're good to go. That just repeats until I get through one of those passes, then lets me know that left is where I need to swap my pivot to. And so that's my very last step, just as I saw when I was cleaning up. I'm going to swap left with the pivot, so that puts pivot into its right position, and everything to the left of the pivot then is, of course, less than the pivot. Everything to the right is, of course, greater than. Or I should say more appropriately, everything to the left is not greater than the pivot, and everything to the right is not less than the pivot. Finally, I return left because that was where my pivot is located. So then this feeds this value back, the index of where the partition gets done, right? So that's where the pivot, that the quicksort function that we saw earlier, comes from. It is this left here by the time we get done. So all we do is choose the last item as our pivot. As a recap here, scan from the left for something that is not less than the pivot, scan for the right for something that is not greater than the pivot, and swap it in. So here's another way to look at partition. Right? What have we done here? If you look at the previous version of this code, lines 2 through 13 are lines 3 through 13 are identical to lines 6 through 16. So here is all the body of the original partition. All we've got is something else different here going on at the beginning. And what's that there? You say, well, what if I feel like my data is already sorted? If it's partially sorted, then I'm more likely to find the median of a range in the middle than I am to find it on the right-hand side. Chances are, if I've got data that's partially sorted, it might be pushing me towards a worst case scenario if I'm always picking the thing that's on the right. So in this case, because it's so easy to do that physically, sort of like holding the pivot off to the far right and then just using my left and right pointers, because that's so easy without having to worry about jumping over and around a pivot in the middle. If I wanted to pick my pivot as the middle item, then it would be much more difficult bookkeeping wise to say, well, I'm plussing from the left, but I don't want to compare that to my actual pivot because my actual pivot's in the middle. So I got to hop over that. So the easy way to do that is just always use that element at the right. But if you want to use a value that's not the value from the right, you can see here that this lines 2 and 3 do something that says, first, let's find the item in the middle of the range, and then we'll swap it to the end of the range so that we can behave as we did previously, right? So this sets the pivot up to be that last thing again. But now the lines 2 and 3, before it sets the pivot up to be that last item, it changes that last item to be holding what was in the middle of the range when this particular partition started. So this is just another way to do it, right? Obviously there's a little bit more overhead in that, but it's a way to improve some quick sorting, right? No matter what, when you're picking an item at random, you still always have the chance to repeatedly pick bad things. So even with this in place, there's nothing to prevent you from always picking a bad object out of the middle, even though you're trying to get something near the middle. So that's how that works. Now, in terms of analysis, we say the cost of partitioning these n elements. What do we have to do for that partition? To find the partition, I looked at things from the left in a linear fashion, plussing my way until I could find something that was greater than the pivot. And then I turned around and I did the same thing from the right, decrementing, minusing. So linear behavior in both of those. And I looked at all the elements I could from the left and all the elements I could from the right until those things met up in the middle. What that means is I looked at every item once that was not the pivot, right? So I would say that the cost of partitioning this is going to be a big O of n. I'm going to spend n work to figure out where I should swap the pivot to so that I can leave that function. So there's my big O of n. In the worst case, after I've done this linear amount of work, I've got n minus 1 things remaining to go. So my T of n is this linear amount of work to figure out where the partition goes, put it into place, and then I've got n minus 1 things left to sort. So that's what it looks like worst case. If you take the master theorem into account here and fire this thing off, I can't master theorem because I've got n minus 1, so I've got to do this with substitution. If I do some substitution on this, I'll end up with something that looks like big O of n squared. And that's what we saw earlier, right? In the best case, when I do this linear amount of work here to figure out where the partition goes, in the best case, I've actually found the median. So I've got this linear amount of work plus half the items on the left and half the items on the right. As I combine this and end up with this function here, you can see that I can master theorem or substitution this one, and I end up with big O of log n. So in the best case, dividing it equally in the middle, I get big O of n log n. In the worst case, I'm going to get something that's big O n squared. There's best case and worst case. What does average case look like? Average case looks like you should take EECS 477. Go very deeply into that. Talk about the way that this algorithm works and some more analysis on it. But for 281, we're just going to give you the values and wave our hands and step off to the next slide. So in the average case, it looks like it's somewhere between 2n log n and approximately 1.39 n log n. So then this is just a constant, and this is a constant times n log n. So the question is, why is partitioning linear? As I do a partition that's linear, right? As I do a partition that's linear, because as I'm looking at all of these elements, right? And this is going to be what my pivot is. I look at this compared to the pivot, this compared to the pivot, this compared to the pivot, this compared to the pivot. Then I'll come here from the right, and each one of these arrows is me comparing something to the pivot. If I do a swap here, then I continue until my left hits the middle or the right or whatever, and that's when I stop. So in this case, I've looked at all of the items in this range once and compared that back to the pivot to determine whether or not I need to swap them with a swap mate. But you still look at all n of the items, n minus 1 of them, that is not the pivot itself. So that's why partition ends up being linear. All right, in terms of memory analysis, how does this work? I've got to use these stack frames for recursive calls. I've got that original algorithm in line 5. I had a call to Quicksort that was followed by another call to Quicksort in line 6. So the line 5 call had to use its own stack frame. If you wanted to be tricky about it, and it's not a bad thing to do, you could say, if I've divided this into two partitions and they are vastly different sizes, I would rather put the one that's longer in the tail recursive call and the shorter one in the non-tail recursive call. So you could do that if you wanted to be a little bit more efficient in terms of stack frames. But you're going to have to make sure that you have to know that stack frames will be used to make this happen. So if your pivoting is going terribly, right, I end up with an edge case where I've picked the greatest in that min-max example. I picked the greatest every time, and I had n minus 1 things to go. So if I do that, I end up with the first stack frame being called with 5 items to sort, and then it calls another stack frame with 4 items to sort, and then another stack frame with 3 items to sort, and so on. I end up with a linear number of stack frames if I've got a worst case pivot. If I've got the other version of it, right? If pivoting is going terribly, I can say, well, if it doesn't change my time complexity, I can still, if I'm always picking sort of like the smallest item, if I always pick the smallest item, then the things to my left are going to be length 0, and the things to my right are going to be length n minus 1. So I won't need additional stack frames there. That one can save me some memory, but it still isn't going to change the fact that when pivoting is going terribly, there's always time is big O n squared. So in this case, I can end up with either a linear or constant amount of memory depending on how which terrible things are doing. But in either case, I'm more upset about this n squared time. we got a typo in here. I've been informed, and now I have to go look up what said typo is. Slide 13. I need 2 recursive calls inside. Oh, yeah, I can see that for sure. All right, so this is a version of Quicksort that I was just talking about. Say, if you're trying to work an average case, you can say, in average case, I'm going to pick some partition, and when I'm really lucky, the left side is exactly equal to the right-hand side. So it doesn't matter which one of those I recurse more deeply into, because they're going to have the same recursion depth. When, however, one of my sides is much larger, so say my randomly picked pivot divides this thing into four pieces, right? And 3 of them are to the left, and 1 of them is to the right. I would love to have my, sort of, let's say there's my partition here. So my partition depth is based on the width of the partition that I'm sorting here. So if this is 3n over 4, and this is n over 4, then you can see that this is going to be a shallower recursion because there's fewer things in there, where this is going to be a deeper recursion, right? So this slide is just saying, what I'm going to do is, before I decide which way I quicksort, I am going to pick the deepest one and make that be my tail recursive call. Because if my deepest one is my tail recursive call, then that one is going to use fewer stack frames. So this is better in memory, right? So what we need really here is a set of curly braces, curly brace there, and another set of curly braces. Because what I'm going to do is I'm going to have to stick in 2 recursive calls. So this is similar to the original one. We saw that I had my partition here, and then I made 2 calls to quicksort. One to do the left-hand side, one to do the right-hand side. All we're doing here is in 5 to say if the region to the left is smaller than the region to the right, then I'm going to use stack frames for the small section, and I'm going to use the individual stack frames for the small section, and I'm going to reuse the tail recursion side on the big section. So here I would have quicksort of A, comma, pivot plus 1, right. All right. And the same thing is true on the other side, so that I can say when things were going the other way, now I would say quicksort. And here I'm going to go from A, left, all the way up to pivot. All right. So there we go. There's a cleaner version of this posted up on Canvas right now. But you see, there's nothing different about it here. All I'm doing is I'm going to be doing the same 2 calls here, right? It's just the order that I do them in that makes one of them tail recursive and one of them stack frame recursive, essentially, right? So if I do them in a different order, say, well, if this is the narrow side, I want to use that for more stack frames because there's going to be likely fewer of them. And if this is the deep side, then that's the one I want to reuse, make that one tail recursive. And so all this does is pick which way to go. For a small constant amount of additional work, you can see here, I'm trading some time for some memory, right? I do a little bit of extra work, it saves me memory. All right, so we've got pros and cons. The advantage is, average case, this is an n log n sort. That's great. That's as fast as any sort can be, is n log n. So average case, it's perfect, right? It's as fast as can be. It's got a short inner loop, which is that linear check to see which one of these things is going to be where my partition belongs. It's efficient in memory, and it's very well studied. So I talked about taking 477 to get into the deep ends of how algorithms work and analysis and stuff like that, much more than we do in 281. You can get into why that average case is somewhere between 2n log n and 1.39n log n. So that's what's good about Quicksort. The bad parts of Quicksort, of course, is worst case is n squared. So average case, this is as fast as any sort can be. Worst case, this is about as bad as all of the other sorts we've ever seen. So there's a disadvantage there. The other thing is it's not stable. You see that swapping something from where my left pointer identifies problems and my right pointer identifies problems. That is a straight shot to instability. And it's very hard to make it stable. So that's something that you give up with Quicksort. Partitioning is something that you have to understand. And if you do it wrong, then things go horribly wrong. But once you get it right, that's great. All right, so how about avoiding that n squared? How can we avoid that worst case scenario? The good performance comes from a good split. So any single choice could be the worst one, but since it's too expensive to calculate the best one, we could try to say, how could I do this a little better? The trick that we just looked at on the previous slide, that's only going to save us memory. It's not going to save us any time. If we got a worst case scenario with this code, in terms of data, this is going to be n squared in time, and it's going to be n in memory. So we're hoping to get to more like log n. When both sides are equal here, I get log n depth on both sides, and that's great. So we're trying to get as close to that as we can. But here in the worst case, no matter what, even if I pick the wide side or the short side of tail recurse, all I'm doing is saving a little bit of memory. It's not changing my time profile. So another way to do this is, instead of doing the full calculation of the median, we could sample the median. One simple way to do it is to just pick 3 elements and then take the median of those 3 elements. The good news about that is I can do that in a constant amount of additional time. One simple way to do it is pick the first item in the range, the last item in the range, and the middle item in the range. There you go. You can calculate that in constant time. And then with a couple of additional comparisons, you can figure out which one of those items is the median of those 3. So then if I use that and swap it to my far right and say, this is my new pivot of this range, I'm at least guaranteed that no matter what, there will always be one item on each side of the pivot. So that's the way to do it. It's actually a pretty powerful technique. It's going to give you better performance. I think the STL G++ STL version of that does something similar to that. It does a pick 3 elements, finds their median, pick 3 more elements, finds their median, pick 3 more elements, finds their median, and then finds the median of those 3 medians and say, this is what I'm going to use in my pivot. So now I'm guaranteed that there's going to be at least 4 elements on either side of my pivot, no matter what, even if it's sort of a worst case scenario. So this is a way to sort of improve it prevents you from ever being able to pick the farthest end of the range. So sampling is pretty powerful, and it can be done in a constant amount of time. So with large sorts, it's a great way to fix things, right? Other improvements that we can look at. In divide and conquer, we understand that divide and conquer doesn't stop dividing until it gets to a base case. So what that means is we end up with a lot of sorts of size 0 and 1, because they're my base case. It's the only way to get out. So if I've got 50,000 items, I'm going to do a lot of sorts of size 0 and 1, like more than 50,000 of them. So we could speed things up by saying, how do I sort small arrays? The best way to sort small arrays is use insertion sort. So when I get down below a certain size, I'm just going to bail out of even trying to quicksort. And a certain size is something that you've got to empirically define there. So once I get down below 20 items or 10 items, you can say, it doesn't make any sense to try to quicksort this. Insertion sort is actually faster. It's not better in terms of asymptotic complexity, because insertion sort is still always n squared. However, with small data ranges, insertion sort is the fastest sort, regardless of complexity. So a small data range with 10 items, for instance, the big O of n log n is less than the big O of n squared, but quicksort is not faster on that range than insertion sort. And it has to do with the way that the data gets located, and because we're moving so close and moving data that's close, insertion sort ends up being faster. So we could bail out somewhere around 16 or 32. I think that the way that the G++ STL does it, if it's less than 16, it dives in and does a different sort there, right? It's going to insertion sort that thing. Here's an example of how sampling goes. You see I've got this range of data here, and I'm going to do a sample just by picking the first item, the last item, and the one in the middle. I'll take the median of them, which is 14, use 14 as my pivot, so then I'll swap 14 and 5 here, and then as I continue moving forward, I end up with a decent little split there, because with 14 as my pivot, I end up with 5 elements less than 14 and 9 elements greater than 14. So it's not a perfect median, but it's better than probably taking something else, right? So because this is still a constant amount of additional work, it doesn't change the overall complexity of how Quicksort works, right? Identifying the first item, the last item, that's easily done. I just get those values almost from being passed in there. And then with a little bit of math, I can locate this median element, and then 2 comparisons tells me which one of these is the middle one, and I'm good to go. Another way I could do it is I could do random sampling. Right here, I'm not picking the first, middle, and last. I can just pick any 3 from inside there. Problem with random sampling is you've got to generate random numbers, so that can often slow you down a little bit. And we're using the best of 3 here. You could also move that up to any sort of odd number set that you like. So I could take the best of 5. If I took 5 items, I'd have to do more comparisons, but then I would be guaranteed that my pivot would always have at least 2 things on the left-hand side and at least 2 things on the right-hand side. So both of those are moving me away from getting to a worst-case scenario. Best of 7, best of 9. As I mentioned, I saw that an implementation did a best of 9, but it was 3 best of 3s. And that just gives you a pivot that's right there, somewhere near the middle. All right, so here is our summary on Quicksort. It's an n log n times sort. We're good with that. It's efficient based upon the selection of the pivot. Sometimes it's better, sometimes it's worse. I can use the middle key or I can use the last key. We looked at sampling and other creative ways to sort of get around this. There's other ways that we can tune it. We can use another sort when the partition gets small. We didn't discuss 3-way partitioning, but that's also a thing in Quicksort. So if you would like to do some additional research before you get into 477, go check out the Wikipedia page on Quicksort, and you can learn about 3-way partition. That'll talk about some other things you can do. All right. Intro sort. This is a question we get regularly is, what does the STL use? Standard sort from the STL is an introspective sort. And introspective is to think about yourself, right? So an intro sort is one that is doing some meta work to see how the sort is going. G++ and Visual Studio use one. So in intro sort, the way that it's often implemented is when the region is small, it uses insertion sort, because we know that that's the best way to do things. Otherwise, if the recursion depth is too high, you end up using heap sort, right? So what do you mean by too high? Well, I know that in the ideal case, if I continue to divide my data segment in half and in half and in half and in half and in half, that I'm only going to go log n stack frames deep. All right, so log n is my target because that's my best case. So if the recursion depth goes above log n, that's probably not the worst thing. But if it goes above 2n, we're getting pretty deep here. We could be on our way to a worst case scenario. So that's kind of one of the metrics that is often used with trying to figure out when is the recursion depth too much, right? If the recursion depth is more than 2 times optimal, let's say just forget this recursive thing and use another slightly slower but guaranteed n log n sort. So once my recursion depth gets too high, above 2 times n log n, say, then we're just going to take that region and heap sort it. Heap sort's a little bit slower than quicksort, but it is guaranteed n log n, and the remainder of the work that you have to do is fixed in at n log n. Otherwise, if my region isn't too small and my depth isn't too deep, we're just going to use good old quicksort. So that's one way to do it. Some versions of the STL use intro sort. Other versions of the STL will use tim sort, and that's not something we're going to cover, but another good thing to go understand, or at least have a background in. Go check out Wikipedia, look up tim sort, and do some reading there in your copious amounts of quarantine free time. All right, sorting algorithms in time. We used our large-scale classification, our big O analysis. We saw that our sorting algorithms that have worst case n squared time, that was bubble sort, insertion sort, selection sort. They were worst case n squared time. Quicksort was also worst case n squared time. Average case, however, was n log n. Heap sort was our heap-based sort. That was n log n in the worst case. How about memory? Memory usage. We saw that in bubble sort, insertion sort, selection sort, all we were doing was either a swap or a move, and that never really required us to hold a lot of values. It just required us to hold one. The value that we're moving into place or the value that we're swapping into place, and then doing a single right there. So those had constant amount of memory. How about heap sort? What do we think about the overhead of heap sort? Remember how heap sort went? We first built a heap. Memory complexity, constant. Then, as we sort of deconstructed the heap and put our big item at the end of the container, we just did a fix. So this was a bunch of swaps. Heap sort gets done with a bunch of swaps. So this ends up being big O of 1 overhead. There we go. That's right. Quicksort. If you look at the algorithm, you saw that we had one variable inside of quicksort, right? That was give me the location of pivot. So it seems like I only had 4 bytes. I just needed that index. If I look a little bit deeper into partition, you see that I calculated a median there. So I had an additional variable that was pivot. So it looked like a constant amount of memory because both of those functions only had one additional local variable. However, we can't forget that those stack frames are being called recursively. So Quicksort's extra memory was, I guess in the best worst case, was a constant amount of additional memory, right? But in the average case, so this is best worst. I don't know. That's real case, right? We had worst case performance, but the best version of worst case performance, I would end up with a constant amount of memory. In the average case, I would end up with something that looked like log n stack frames. And in the worst case, I would end up with a big O of n additional memory. Right? So this is the worst. All right? How about stability? Do we remember what stability was? This happens when the same key values remain relatively located. So if I have a 4 early in the data section and a 4 later in the data section, by the time I get done sorting them, they'll be next to each other. If the left 4 always stays left of the right 4, then we call that algorithm stable. So bubble sort, we knew that was stable, right? Insertion sort, we said that was stable. Selection sort, not so much. Heap sort, how do we figure out heap sort? All right. So heap sort, because of these fixes, don't necessarily end up stable there. And quicksort, definitely not stable. All right. So there we go. Self-study here. This is the things that you can work on to make sure that you understand this lecture. We need to illustrate the worst case input for quicksort. Can you find that? There's more than one worst case. We looked at one. There's more than one. Look for some of those and figure out how many there are. Explain why best case is not linear. If I do my pivot selection in constant time, what happens if I do a little bit more work and do my pivot selection in linear time? Does that change the complexity? Right? What if I improve quicksort with linear time median selection? Can you do that? All right. That is that.